And the answer is, well, it's smaller than what I got at the corner point. -4 is less than 0. So I got something smaller when I went up here. That means that this corner point is not a minimum, i.e. there's no minimum at all. So this means that there is no minimum, because I got something smaller when I went up here than what I got at the corner point. If I were to keep going and pick a bigger, like 0, 10, I would get -10, and I would see that it gets even smaller. And as I go further and further up, the value of the function gets even smaller. And so we can see, thinking of it that way, that clearly there's no minimum, because as I go further and further up, the function gets more and more negative without stopping ever. So there's no way there can be a minimum value. But we would not have known that if we hadn't tested a point up here. So that's what we need to do that for, to make sure. Okay. Now, the question remains, though, there's no minimum. Could there be a maximum, though? As I go further and further up this y-axis, I get really big negative values. So it gets smaller and smaller. But I never get above 0 when I do that. So maybe 0 is a maximum, though? Well, we need to test another point. We still haven't checked on this piece that goes off forever. So let's do that. Let's take another point down here. I don't know, how about 4, 0 on the x-axis? And let's test that in our function. So we'll take the point 4, 0 and plug it into P. I'll get 4 minus 0, that's 4. That is bigger than 0. So when I go this way, I get things that are bigger than what I got at the corner point, which means there's no maximum either. Because as I go further and further this way, the values of the function just get bigger and bigger and bigger, and they never stop. And so there's no way there's a maximum. So it turns out in this example, there is no minimum and no maximum. We don't have either one. And so if you were asked to minimize or maximize your objective function subject to these constraints, we actually wouldn't be able to do it. These constraints are not enough to guarantee that there's a maximum or a minimum. So we'd just kind of be toast. So if you had a problem like this, that said maximize or minimize this subject to these constraints, and you got to this point where there's no min or max, I mean, you basically just have to say this: there's no minimum or maximum. There's nothing more we can do. If we wanted a min or a max for this to exist, I need more constraints. I don't have enough in some sense, because this is unbounded and it's just there's no min or max. So, okay. So I'll pause here again for questions, if anyone has any. Okay. So this is a typical example, but maybe it's like, I don't know. Again, it's like the simplest one I could think of to illustrate. I want to do another one that's just a little more complicated, with a little more constraints thrown in to see something else, how else this kind of thing could fail. And here's something you should think about. Is it possible, if I have an unbounded feasible set, is it possible that my function still has both a min and a max? Can that happen? So that's just a question for you guys to think about. If I have an unbounded feasible set, is it still possible to get both a minimum and a maximum? We just saw that it's possible that you don't have either one. Is it possible that I could have both? That's a good question to think about, if that's possible. Anyway, let me show you another example. Here's our objective function this time. We're going to take x squared plus y. So x squared plus y is our objective function. And our constraints will be the following: x greater than or equal to 0, y greater than or equal to 0, y less than or equal to 5, and y less than or equal, greater than is what I want. Greater than or equal to negative x plus 3. So these 4 inequalities will be my constraints. And again, we're just going to look for both the min and the max of P subject to these constraints. We just want to see what happens. And so, of course, it's going to end up being that this feasible set is unbounded. Let's see what it really looks like. Let's graph these inequalities, this system of inequalities, and see what we get. So here are my axes. Okay, so again, these two together tell me that I'm in the first quadrant. I'm to the right of the y-axis, and I'm above the x-axis. So I know I'm up here again. But I have these other ones I have to take care of. So y is less than or equal to 5. Where is the line y equals 5? Well, if you guys remember, y equals 5 will give me a horizontal line with y-intercept equal to 5. So I go up to 5. I'll draw this a little higher up, actually. I go up to 5 on the y-axis, and I draw a horizontal line. And when I say y is less than or equal to 5, that means I'm going to shade underneath that line. So far, I'm in this like strip part over here. To the right of the y-axis and under between these two horizontal lines. This is where I'm shading right now, so far. The last bit is this inequality here. Y is greater than or equal to negative x plus 3. I have to graph this line, y equals negative x plus 3. This is in slope-intercept form conveniently. So I have a y-intercept of 3 and a slope of negative 1. So I have to go up to 3, and then I have to use the fact that I have a slope of negative 1. So maybe I should 1, 2. Where's the tick mark for us? I have to use the fact that I have a slope of negative 1, which tells me that when I go to the right by 1, I go down by 1. So start at 3 on the y-axis, and then to the right by 1, down by 1, right by 1, so forth. And then I'll draw in the line. Okay. Now, the final question is, where do I shade with that last one? And it turns out, if you were to test a point, so pick some point not on this line, it turns out I'm going to shade above this line. So I don't know, test a point 0, 0. If I put in 0, I get 0 is greater than or equal to 3, which is false, right? 0 is not greater than or equal to 3. That's a false statement. Since 0, 0 was down here below the line, and I got a false statement, I should instead shade above the line. So it looks like I'm shading above this line and between these two and to the right of this one. So I'm shading in this region here. That is my feasible set. So here's the feasible set. And it goes on forever to the right. So there's my feasible set. Bounded by these lines, and then it goes on forever to the right in between the two horizontal lines. Okay. Cool, so it's clearly unbounded because it goes off forever to the right. Unbounded thing. And so now the question is, where are my corner points? How many corner points do I have? So I'm looking for corner points touching the shaded region. Let's see, I see one here. I see one here. And I see one here. And that's it. So there are 3 corner points. And we're sort of in luck this time. Normally I would tell you, go solve for them. Set up the systems of equations and solve for them. And you're welcome to do that here as well. But we're actually in a situation where they're pretty easy to tell what they are without having to solve. Our corner points look like 0, 5 for this point. This one is 0, 3. And this one is 3, 0. So those are my 3 corner points. Okay. So what I want to do now is, of course, plug these into our objective function, see what we get. So let's plug them in. I'm going to make a table, perhaps. So when I plug in 0, 5 into here, what do I get? Well, I get 0 plus 5, I get 5. When I plug in 0, 3, I get 0 plus 3, that's 3. And when I plug in 3, 0, I get 3 squared plus 0. 3 squared is 9, so I get 9. So at my corner points, the values that I get are 5, 3, and 9. So now the question is, are any of those a minimum or a maximum of this function? And again, we can't say for sure yet because the feasible set is unbounded. And so I have to take two more points, one from this infinite part, this unbounded part, and one from this unbounded part, and I have to plug them in. So again, the points that we take that aren't corner points have to be on unbounded parts. So like I could take one from this part up here, and I could take one from this part down here. So let's try those, some points from those parts, and see if they're bigger or smaller than what I got from the corner points. So let's take a point up here first, just because, why not? So we'll take a point up here first. This is on the line y equals 5. That means that I just need to take a point that has a y coordinate equal to 5 and is to the right of this corner point, because I want something different from the corner point. So I don't know. Let's try, just pick some positive number for the x coordinate. It doesn't matter. How about 3? And then the y coordinate has to be 5 to be on that line. So if I'm picking a point on this line, the y coordinate has to be 5. Okay. So we're going to try the point 3, 5. This point up here. 3, 5. Let's try that. We'll just plug it into our function and see what happens. So I get 3 squared plus 5. 3 squared is 9. 9 plus 5 is 14. So p equals 14. Okay. So let's compare that now to what we got at the corner points. I got 14 at this point. But at the corner points, everything I got was less than 14. I got 5, 3, and 9. Those are all less than 14. So what does that tell me? The fact that I got something bigger away from the corner point tells me automatically that there's no maximum. Because again, the maximum, if it existed, has to happen at a corner point. And I have just found that I got something bigger than what I got at all the corner points. So therefore, there's no maximum at all. So there's no max. There is no max. And again, if you were to just take points on this line and go out forever, as you kept getting further to the right, the value you'd get from the function would just get bigger and bigger, never stop growing. So that we could see that there really is no max. Okay. Well, okay. Maybe there's a minimum though. I don't know. Let's find out. Let's take a point from this other unbounded part down below. That's on the x-axis, and I need to stay to the right of the corner point, which is 3, 0. So I don't know, let's take 5, 0. That's a point on this line that's different from the corner point. So we'll try 5, 0. Yeah, 5, 0. So let's plug that in and see what we get. So that's 5 squared plus 0. 5 squared is 25, so p is 25. Okay, p is 25. Let's compare that again to the corner points. 25 is again bigger than everything I got at the corner point. Bigger than the thing at the corner point. Oh, so what's that telling me again? It's just telling me again that there's no maximum. That's all it's saying. This is bigger than these, so these are not the maximum. So this really didn't tell me anything new. It just tells me again that there's no max. So again, there's no max. We already knew that though, from the other point. So, okay, there's no maximum. But notice then, if I take points on either of these unbounded parts, I just get things bigger than what I got at the corner points. I don't get anything smaller than what I got at the corner points. And so what that tells us is that there is a minimum. And the minimum is exactly the smallest value that I got from the corner points. And that happens to be 3. 3 is our minimum. So there is a minimum, and it's 3, and it happens at the point 0, 3. So here's our minimum point. Okay. So just to summarize this problem, we knew there's no maximum because as I go further to the right, my function gets bigger and bigger without bound. If I'm on these lines, it just gets bigger and bigger. But it only got bigger and it never got smaller. So that means that there is a minimum